Hi, I'm now Koshimoto from Osaka University. Today, I'm talking about free-floating planet mass function measured from the MOA-29 microlensing survey and expectations for Roman based on our results. At first, I didn't plan to emphasize this, but now that I heard an interesting talk by Sam and Will, I want to note that the mass function, this is a mass function for free-floating planet candidates. That means it includes actual, free-floating planets, as well as a very wide orbit planets with too far host to host microlensing. Okay, so I think I can almost skip this slide, but free-floating planets, or FFPs, planetary mass objects that do not have host stars. And as for the formation scenarios, in-situ formation might be possible for massive gas giants, but most of them are thought to be formed in protoplanetary disk and then gravitationally scattered due to other planets or stars. And direct imaging can be used to detect nearby young massive FFPs like the upper right figure. But only the gravitational microlensing can be used to detect all those small FFPs like the lower right one. And there has been 20 FFPs, FFP candidates discovered so far. And I think I can skip this slide also, but basically what I want to remind you is that in most cases, in most microlensing events, the only observable we can measure is this event time scale, TE, which is a function of 3 parameters. Yeah. And unfortunately, we cannot measure the lens mass in most cases. But because the TE is proportional to the square root of mass, we can detect the FFP candidates by measuring the short time scale events like the less than 1 day. So to detect such a very short time scale signal, and also because the microlensing is a very rare phenomenon, we have been performed a high cadence survey towards the galactic bulge using the MOA-2 telescope in New Zealand since 2006. The mirror size is 1.8 meter and the field of view is 2.2 square degrees. And this is our survey fields, 50 square degrees of the galactic bulge. And Roman field is in field 5 and 6, somewhere around here. And we are observing every night in the bulge season from 15 minutes cadence to 1 day cadence, depending on the fields. So in this study, we systematically analyzed MOA-29 data taken from 2006 to 2014. And we used the difference image analysis technique to identify variable objects in more than 260,000 images taken over 9 years. And from the light curve, we selected microlensing events based on certain criteria. And actually, there was a previous study by Smith et al. 2011 for just 2 days from 2006 to 2007. And there are several improvements from the previous study. One of them is we removed systematic errors correlated with air mass and sink. And these are mainly due to differential refraction. And another one is we consider the finite source effect, which is a high order effect. And this affects especially for the short time scale events, including the FFP events. So we needed to consider this carefully to estimate the detectability of the FFP candidates precisely. And here is our selected about 3,500 events shown as a function of event time scale t, ranging from 0.057 days to 757 days. And actually, most part of this distribution can be well explained by a model of our galaxy that considers only star and brown dwarf component. But it is obvious that this star plus brown dwarf model cannot explain the short portion of this distribution. So these 6 are FFP candidates. As I said at the beginning, I said candidates because it could be very wide orbit planets. I don't introduce all of them, but let me introduce the shortest one. So the left figure shows the light curve of the shortest events, where we captured magnification that lasted only 6 hours. And the right figure shows the posterior distribution of the lens mass from our Bayesian analysis using a model of our galaxy as priors. We tried 2 different priors for the mass function, and both indicates that lens mass is a terrestrial mass. So we concluded that this is the second terrestrial mass FFP candidate to date. Okay, let's get back to the T distribution. And since it is more difficult to detect shorter timescale events, we need to correct for detection efficiency to retrieve the intrinsic distribution. So we performed the injection and recovery tests of 64 million artificial events using the same selection criteria that we use for actual event selection. And the right figure shows the computed detection efficiency. And this green histogram in the left panel shows the number of events divided by the detection efficiency. And this already suggests, there is a large number of FFP population. So let's estimate how abundant they are. So to estimate the FFP mass function, we model the observed distribution by combination of the detection efficiency, the stellar density and velocity distributions in our galaxy, and the mass function ranging from the 10 to the minus 7 solar mass to 120 solar masses. So we use the broken power law model for the star and brown dwarf mass region. And separately, we use a single power law model for the planetary mass region. And we use these, these 3 red parameters as fitting parameters: the slope for brown dwarf mass region, the slope for planetary mass region, and the normalization for the planetary mass function. And we performed the MCMC to estimate these values. And I don't think, just looking at these values give you much information. So let's plot the mass function. So this is a mass function over more than 8 orders of magnitude in mass. And the x-axis on the bottom shows the Earth mass. And the x-axis on the top shows the solar mass. And the y-axis is a dn over d log m in the units of pardex per star. And the green one shows our planetary mass function. And the shaded area corresponds to 1 sigma uncertainty. So from this, we found that low mass FFPs are much more abundant than high mass FFPs. And the total amount of FFPs down to 0.33 Earth masses are about 17 FFPs per star, or equivalently 69 Earth masses per star with large uncertainty. And this figure looks even more interesting if we plot the mass function for bound planets. So this gray one is for the microlensing planets taken from Suzuki 2016. And the mass function has a peak around the Neptune mass. So by comparing the green one and gray one in this figure, you can find the the bound planet is there are more bound planets than FFPs at masses larger than Neptune mass, whereas there are more FFPs than bound planets at masses less than Neptune mass. So this might indicate that small planets are likely to be ejected from their birthplace, while massive planets are likely to remain. Okay, so finally, let me talk about the expectation for the Roman survey. So the expected yields of FFPs by the Roman survey is already estimated by Johnson et al. 2020, and they predicted that Roman would discover about 250 FFPs, including about 60 with smaller than Earth masses. But this estimate is based on free floating mass, free floating planet mass function assumed it is the same as the mass function for the bound planets because there was no usable FFP mass function at that time. So we re-estimated or renormalized their values using our mass function. The right figure shows a comparison between our mass function and their mass function. And actually, the mass function used in Johnson et al. Well fits in the 1 sigma region of the measured mass function. But the important thing is we use the actually measured mass function for the free floating planet candidates. And we estimated that Roman will detect 280 to 2,100 FFPs, including about 30 to 1,600 with masses lower than Earth masses. So obviously there is large uncertainties, but these large uncertainties actually correspond to the room that Roman can improve the mass function. So that means Roman will measure the FFP mass function much more precisely. So here is a summary. I don't have time, so I will leave this summary and take your questions.
Thank you, Naoki. Question for Naoki.
So I imagine this was already being discussed within the survey design group, but there was a paper by Andy Gould from a week ago arguing for, smaller area, higher cadence, specifically to get better sensitivity to the lowest mass free floating planet. So I'm just interested in your reaction to that idea or other things that you might want to modify in terms of the survey design, given what you're finding.
Yeah, actually, I have to say I'm attracted by the Gould's suggestion, and so as you can see from this table, for example, for the 0.01 Earth masses, expected number would be, the uncertainty is more than, I don't know, 5 or 10 orders of magnitudes. And if we have, more than one detection, it means Roman can put a constraint at this region. But if it is less than 0, so there is still, large uncertainty from the 10 to the minus 4 to, 0.1 or something. So I think, including this probability or possibility that we can detect more than one planet at this mass range is important. So but obviously we need more discussion to decide the survey strategy, but yeah, I think his Guru's idea is, worth considering carefully.
Okay, let's thank Naoki again.